Welcome to the March 2026 meeting. Especially anybody new. Do we have anybody new here? Welcome. Welcome. You should introduce yourself since we don't know you. Welcome to all the new people. We try to be a friendly group. There's a sign up sheet in the back too. If anybody didn't sign up already, just so we can keep track of people. And I've already forgotten. So I guess we'll go ahead and move to the next slide. All right. So our safety slides are all wrong because we're in the wrong room now. But yeah, be careful of cables, and I've got the chairs set up in funny places, and the iPads are over here. Um, Anybody here CPR certified? We got a couple of people. Who wants to be a 911 dialer? Dana will be. Excuse me, the new guy over there. We've got a fire extinguisher back there in the corner and one actually right here. So that works out. Remote attendees, please be aware of your surroundings. Don't trip over stuff. Fire exits are around the corner here on the left of the restrooms. And we are not an Explorer on 4. But as I think I mentioned last time, because of the changes to the elevator down there, for at least the foreseeable future, we will be on Explorer on 4. So we won't be going back down to the A level any longer until the museum tells us otherwise. So, yes.
Yeah, I can be loud. They have people that will show you where to go, and Explorer on 4 is actually on the fourth floor, and it's right by the elevators, so it's real easy to find.
Yeah. So basically, when you get here, normally, much kind of like tonight, except without all the outside walking, you'll come into the main doors over in the other building when it's not closed, and just wait outside. Somebody from inside will see you, let the door open, and point you to the elevator so you can go ahead and walk over to the elevator. And usually we're in groups of people anyway. So, all right. So we got some upcoming events. So we've got First Fridays, depending on weather. That's going to be next Friday. We've got the Willard on the 8th. Our next RAC meeting is actually just in 2 weeks on April 10th, and we will be having a social for that. We've also got the Wild Ideas Expo. Steve, I don't know if you wanted to mention anything about that. I'm guessing not. Okay, so a daytime solar event on the 11th and 10 to 2. Okay, so that will probably be 10 to 2. Check the calendar for info. And the very gracious Herrings have offered up a herring star party with pizza on the 18th, so 3 weeks from tomorrow. And then, pardon me. And then we've got Apex Friendly Elementary School, STEM Night on the 22nd, statewide Star Party events. There are several of them on the 24th. There's American Tobacco Trail, White Deer Park, or sorry, American Tobacco Trail in Apex, White Deer Park in Garner, Imagination Station in Wilson, and then Prairie Ridge in Raleigh. So maybe not. Okay, so the Prairie Ridge is canceled then. Sorry about that. As of yesterday, it was still live. Okay. All right. So tonight. Okay. So tonight's presentation, we have Alex McConahay with us on Which Way is Up. Everybody thinks it's that way, but depending on where you are in space, it might be somewhere else. So he's been an amateur astronomer in the Riverside, California Astronomical Society for the last 3 decades. He's got nearly every office in that club. Was on the board of the RTMC Astronomy Expo and the organizer of the Nightfall Star Party, and then founder of the Astro Imaging Channel. So, welcome, Alex. Also, This presentation is narrated, so he won't have his headphones on while we're doing the presentation. So please, everybody, save your questions to the end because we won't be able to stop it. Alex, can you go ahead and start sharing your screen? Affirmation. Okay.
Okay, let's see. So we're ready to begin the presentation.
Hold on 1 second.
Okay.
We're good, Alex. Go.
So you should be seeing Rube Goldberg. And I think you all know, are you seeing Rube?
Yes.
Okay. And what he does is he makes these weird inventions with all sorts of pulleys and wheels and inclines and screws and helixes. And they do all sorts of weird stuff. And if you guys can figure out how this one works, send me an email and tell me about it because I still, after all the times I've shown this, I really can't figure out what they're doing here to make all of these things work just the way they should. I mean, Newton says everything goes downhill, right? That's how he said after he got hit in the head with the apple. But you know what? I think Goldberg won this one again. I mean, Rube Goldberg, he's smarter than Newton. It's really a simple question. Which way is up? And I can give you some pretty practical advice. I mean, um, that's up and that's down. And no matter what else you hear tonight, that'll probably pretty much be true as a practical matter. Nothing that I'll say tonight should affect you in your day-to-day life. But at the level at which scientists need precision, it can get pretty complicated depending on how the term is used and the context. So let's be clear, up is a direction, and to have a direction, you must have dimensions like length and height and depth. And yeah, we all know that there are other dimensions. You got to have at least three, but you'll have four if you count time, and more if you count special physics and mathematics, and even if you're into science fiction and fantasy. And depending on which way our three standard dimensions are turned, you may lose track of which way's up. Our three-dimensional model here can be called a context or a frame of reference. What astronomers and many other scientists need to do is establish a frame of going, and we're going to talk about several ways to define a frame of reference today. Up is just one direction in that frame of reference. Let's say our frame of reference is acrobats in a circus. So here we've got acrobats in a circus. And we got A, he's the strong man. And we got B, he's got perfect balance and can balance on his buddy's finger there. That's pretty good. We got the hard-headed guy. And then we got D, the great no leanie. He doesn't lean back and forth anyway. He just can hold his balance right there. Isn't that great? Sure. In that frame of reference, they're just acrobats. Or we can be more practical and change our definition of the frame of reference. Let's imagine the context is that we're instead in the International Space Station. And all we've got is a couple of guys and some photoshopping showing off. So context is important. Are we living in a circus or a space station? We have to establish that. Within that frame of reference, we must have movement. I'm going to posit that without movement, a change in place of one thing to another. Just a second here. I have to get rid of something in the Zoom. There we go. We have to decide that there has to be some kind of movement. If you don't have a movement, then there's no thing to worry about direction and therefore no up. If nothing is moving, the concepts of forward, backward, down, up don't really seem to matter. But no matter what, nothing that I'm going to say is going to be definitive. Everything has its own complication. So let's get into some of that. Let's take the first one, forward direction. Let's face it, we can say up ahead, up front, I'm moving up. All these are related to the direction we are moving forward. Oops, excuse me, got a timing problem there. We're moving forward. All these ideas give us an idea that we're moving up. But which way is forward? We have two problems with this, both the frame and the direction. We have to have a frame of reference, and I contend that there is no single fixed frame of reference. And even if there were frames, the irregularities of motion through them would make it impossible to name one forward to be our up. Let's just look at these types of motion that we're going through all the time, these irregularities. The list over here, rotation, revolution, precession, and all that, gives us a lot of ideas that we're not really moving straight ahead, no matter what else is happening. I mean, you all know that the Earth rotates once a day and that it revolves around the sun once a year. But you know, the sun is not exactly standing still. As it moves through space, we fly through the galaxy with the retinue of planets, moons, asteroids spinning around the sun as we go. We're part of a cosmic helix, a screw threading our way through the universe. Not nearly as easy to tell which way is forward in this context, is it? Yeah, that's right. We're spinning our way around the galaxy. We're not moving in a straight line. We're actually orbiting its center and going around about once every 500 million years. And, you know, we're not just moving around it like this, but we're also body surfing its waves, bobbing up and down every 100 million years or so, such that sometimes we're a touch above the plane of the galaxy, and sometimes we're a touch below the plane of the galaxy, whatever below and above might mean. But there are other complications besides the somewhat predictable motion of orbits and cycles. Each star has its own proper motion and which way it's going to be moving relative to the others. Notice in these simulations, the stars are not moving the same directions at the same speed. They seem to be just wandering around aimlessly. Constellations and asterisms we know today will be whacked out of shape through the ages as each makes its way through the galaxy. Here's where we were when we came out of Africa. That's the Big Dipper. Here it is now. And down here in 100,000 years, that's what our Big Dipper is going to look like. And it's not just the galaxy, it is the galaxies. The whole universe is filled with galaxies, each boatload of stars sailing along on its own course through the eons. And occasionally they run into each other. Whatever regular motion they might have had is just torn apart. Everything becomes a huge mess. They may establish some sort of equilibrium for a while before running into one another galaxy, or even the same ones. Tell me, which way is forward on a star going through such disruptive motions? Here's an example. Astronomy books tell the story of Arcturus, the fourth brightest star in the sky. It's a visitor. It's just passing through our part of space. An orange giant 37 light years away. Arcturus is an ancient population 2 star, 10 billion years old, metal-poor member of the Milky Way's halo that just happens to be diving through our part of the galaxy's disk. But it turns out that that's not half the stories. Arcturus seems to have come from another galaxy. Arcturus was likely born in a dwarf galaxy that fell into the Milky Way and has now almost completely dispersed, being eaten up by the Milky Way. Here's an illustration of what scientists think might happen to a dwarf galaxy, Sagittarius A, that was eaten by the Milky Way. Arcturus is speeding through our stellar neighborhood. It's going about 120 kilometers per second relative to the Earth. 500,000 years ago, it was too distant to be visible with the naked eye. And 500,000 years from now, it will already be faded from view. It's a great proper motion, and it's part of the Arcturus moving group. It's a bunch of 53 stars that share parallel galactic orbits. They all have similar metallic compositions. Since this ancient emergence, the astronomers say, Arcturus and its siblings have traveled around the Milky Way about 100 times in their elongated orbits. Their up is different from ours. Astronomers have known for years that something seems to be pulling our Milky Way and tens of thousands of other galaxies towards a certain point. And they've identified it someplace up here in the Great Attractor, near the Centaurus cluster. It's a huge volume of space that includes the Milky Way and superclusters of galaxies flowing towards a gigantic unseen mass. It's right up here. It's called the Great Attractor, some 250 million light years from our solar system. Is that where forward is taking us? Is that up? And I really haven't seen much about this next point, but it does confuse the story even more. This image shows the two hemispheres of a spherical mapping of the cosmic microwave background. New research, and I haven't seen it duplicated in various or talked about very much, examining the velocities of type 1a supernovae suggest faster expansion in the northern hemisphere of the universe, challenging the cosmological principle that the universe is expanding universally uniformly in all directions. If the universe itself is expanding to the north, is that where forward is? Is that up? There are simply too many motions involved to say up is related to forward. So we must have something else. Let's try north as a definition of up. After all, we can head up north or down south. Next summer, I'm heading up to Alaska. Next winter, maybe I'll go down under. Pretty clear for most of us that north is up and south is down. Unless, of course, we're from down there. You notice they like to have this map reconstructed so that Australia, South Africa, and Tierra del Fuego are at the most important part. But they seem to have fooled themselves because you know what? If they were to just turn the maps upside down and say keep the same Mercator projection, they're still cheating themselves. You see, that Mercator projection makes everything a lot different. They're a lot bigger when you actually put them on the same Mercator projection that you see on normal maps. But let's get into what is north. In some societies, north is not the top. Okay, here's a T&O map, and people made these for centuries. This is one, and here's an illustration of what it says. It basically says that Jerusalem is in the middle of the world, and Europe, Africa, Asia, with the Nile and the Mars Magnum, or the Big Sea, Mediterranean, and this 10A that they call here is the Don River. So that's what forms the T in a T map. But you can see that north is not up here. And see this is where the sun rises, and it was very important to the Navajo. So when they made a map, east was up. That was their most important part. That's where they put it. But enough about maps and up. Can we define north? We can if we have motion. In this case, the motion of rotation. See how the planet is moving in one direction? Point in that direction with your right hand and stick your thumb up. That's where north is by definition. Your fingers point east, the direction of rotation. Your thumb points north. That is the definition of north. But you know, scientists, they can't leave simple things alone. They have complicated what north means. They give us at least three types of north. The first is geographic or geodetic, the true north. This is the old right-hand rule. We spin to the east and our thumb points north. It's based purely on the rotation of the Earth. In this context, true north is the point on the Earth that is the center of this spinning. It's the poles. The second is astronomical or celestial north. It's based on where the northern end of the pole is pointed up in the sky. Here's a picture of a Joshua tree. We got a lot more of them around us than you guys have back there. And you can see all the stars appear to rotate around the North Star. We know that it's just an illusion and the Earth is doing all the rotating, not the stars. But we get it. But you see this star right here in the middle? That which everything else revolves around? This is our North Star. It's where our astronomical or celestial North Pole is. The difference between the geographical and the astronomical pole is where it is marked. The geographic pole is marked by a spot on the Earth, and the astronomical or celestial pole is a point in the heaven, the place to which our pole is pointed. We say our astronomical celestial pole, what's that? Consistently points to a position in the sky, and usually what we call the North Star. And finally, we have magnetic north. The Earth is a huge magnet, and one part of this magnet pulls to the north and the other to the south. Simple enough, right? No, it's not simple. None of this is that simple. That's the whole point of this presentation. There are, in fact, many cycles of wobbles in our Earth that are piled on each other. That's where our North Pole is actually moving from time to time. Notice these cycles cause the pattern to appear irregular. And note how the path of the North Pole of balance varies by some 70 feet. Notice furthermore that the center of the circle is not at the intersection of 180 and 90 degrees. Nutation is the natural tendency of a spinning object to have its orientation deviate through time. There's a cycle of 18.6 years, dependent somewhat on the position of the sun and the moon. There's a cycle of 433 days caused by the atmospheric and sea tides. Many other cycles all impose one on another. They've been noted. There's even a tide induced by these nutations, the only tide not caused by gravitational effects. This gives us a North Pole of balance because the balance of the Earth is slightly imperfect and affected by the physics of rotation, by the movement of other celestial bodies, by tides, and by the lumpiness of the Earth itself. The North Pole of balance wanders, and it is rarely, if ever, at a single geographic point. The Earth is ever so slightly out of balance, and as it wobbles, the North Pole moves around. If that North Pole is wandering around, so are all the other lines of geography, including the lines of latitude and longitude. So if you're on this road in Mexico looking for the sign for the Tropic of Cancer, you'll see how it actually changes depending on where the Earth is rotating. So which way is up? If you've got to be precise, you can't do it that way. Notice how these cycles cause the pattern to appear irregular. And note, oh, I think I've done that. There we go. Click. Click. Thank you. Okay, I'm going to take a time out here. I've been going for a while and telling you that there's no way we can tell all these things because they're different. They all have a measurement of how things change over time. Half a second is the width of 5 ping pong balls as seen from 50 miles away, half an arc second. That's not very much, 5 ping pong balls next to each other all the way out there. How does one know how? But let's go through some examples here of what we can see with 3/4 of an arc second, perhaps. That's how you can tell how far away the nearest star is. And you do it the same way you measure a river. You measure it from one angle on a right triangle, and then you come over and you measure it from a different distance. And if you know this if you know this distance and that angle, and you know your high school trigonometry, you can tell how far away that tree is. Scientists did that with the star compared to where it was compared to the background stars, from when the Earth's position was on one side of the planet to where it was on the other side of the planet. Knowing what this baseline is, they can figure out the distance to how far that star is. Only 76 hundredths of an arc second. So that's how important it can be. What can you find out with 1.75 arc seconds? Well, one of the most famous experiments in the 20th century was Eddington's measure of the difference between the apparent position of a star and its known position during the 1919 solar eclipse. This experiment made Einstein famous and ushered in our way to the nuclear age. Eddington knew the precise position of an actual star behind the sun. And Einstein's theory was that that path would be bent as the light came around the sun, and therefore the star would look like it was out here in this apparent position. Now, what is the difference between the actual and apparent? Well, 1.75 arc seconds, 1 3/4 of an arc second. That's how much an arc second can matter. In order to take images of distant faint objects, Hubble must be extremely steady and accurate. The telescope is able to lock onto a target without deviating more than 7/1000th of an arc second, or about the width of a human hair seen at the distance of 1 mile. Because of such precision, it can measure many things that lead us into scientific discovery. So you can see this little wobble that I talk about, an arc second matters a lot. Okay, you want an example of what you can worry about? How many of you asked your imagers? When you sit there watching your PhD grams, how many are concerned about a 1 or 2 arc second exclusion from your mount? You actually can't see this after all the stacking and such very much, but how many of you worry when focus goes from less than an arc second to 3 arc seconds or something? These things are incredibly small, but they do matter. They don't cause a great problem in life, but if you really want to be accurate about things, you got to get things to less than arc seconds, and that's why you need good directions. So we've given up on the geodretic or true North Pole as a fixed point. There is not one up in there. What about astronomical or celestial pole, that point in the sky around which all the stars rotate? Remember I showed you back here? If I blow this image up and let you see it, you'll actually see that that little point of a star right there is actually an arc. Earlier I defined it as a point. We can see stars rotating around it. It's the North Star, but it's also wandering around the rotating heavens. At the time of the building of the pyramids, about 400,000 years ago, the North Star was a faint little star called Tuban. I think it's down, where did I put it? It's down, I have lost it again. That's Tuban, up there. Okay. It's in Draco the Dragon. Get back there. Get back where you belong. Behave. Draco the Dragon. Tuban is about 10 degrees from the handle of the Big Dipper. All right. So this might help you visualize that within recorded history, the time when the pyramids were being built, the entire Big Dipper was very close to the North Celestial Pole. Over time, precession carried Tuban away from the celestial pole. For many centuries, there was no actual pole star. Jesus had no pole star. For the past thousands of years, Polaris has been drawing nearer to the actual celestial pole. As our axis continues to shift, Polaris will come even closer to the actual celestial pole, and it'll make its closest approach to the 22nd century about 130 years from now. In some 26,000 years, many other stars will get their chance to be the North Star. A couple of centuries before the year 10,000 AD, Deneb will be the North Star, and that will be a very bright polar star indeed. By the way, this circle moves 51 degrees. Not a particularly good way to tell which way is up. Like a spinning top, Earth's axis moves. It spins and a top naturally precesses or moves such that its polar axis describes a circle in the sky. See how it goes around like that as it moves? As the Earth spins, it precesses a circle of about 23 degrees across the sky, and it takes about 26,000 years to make one circle, pointing as it does to different parts of the northern skies. That's why Tuban is no longer the North Star and Polaris is pretty much it. But Polaris won't be there forever. Shakespeare was wrong. The North Star is not a true fixed resting place. Other planets have different celestial norths. Here you can see the right-hand thumb rule applied, and you will notice that Uranus down here and Venus over here have decidedly different spin directions. As a matter of fact, the scientists have given up on the right-hand thumb rule for Venus and Uranus with their weird rotation angles and declared that regardless of inclination, all planets have north pointing in the same general direction as the sun, at least in our solar system. If you were to point out the different north stars from the various planets, you will find that they are located all over the place. Here's Saturn's, here's Earth. See, it's at the end of the Big Dipper, so forth. So they're all over the place. And another view of that discrepancy, which way is celestial north or up with all these differences? Hard to say. By the way, as you know, the planets move with their orbits in large circles around the sun, and those orbits are largely in a plane. If you were to find a north side of that plane and follow the solar system's polar axis there, you would be led to a north pole someplace up in Draco. Venus and Jupiter also have stars. Let's see, where's these? This is where the sun's polar axis points. And of course, our galaxy rotates with the large stars moving in orbits around the center. Where would you find the north end of that rotation? For us, for a while, it will be up in Coma Berenices, a nice spring constellation. That's called the galactic North Pole. Everything that orbits is a kind of up in the north, but all norths are different and moving because of the variations of the movement in the orbits and their rotations. There was a third kind of up based on magnetic poles of the Earth. With the spinning, somewhat fluid inner core, the Earth itself creates a huge magnet, and any magnet has what we call a North Pole in the south. How reliably can that tell us which way north is, which way is up? Well, let's ignore for a moment that the magnetic poles can reverse now and then on an average of every 200,000 to 300,000 years. And we may be going through one right now. After all, the magnetic field has been weakening for a great number of years and seems to be moving more rapidly. But magnetic reversals are sporadic, can be somewhat local, and with lots of poles showing up at the same time. And they happen over millennia. Let's just pretend that that's not part of our conversation. On the other hand, realize that if in fact that it happens, it says a lot about which way the world is defined if you consider magnetic north being up. Here's a direction here to start with. Let's realize that the spinning magnet does not line up with the spinning Earth. So Earth's geographic and celestial North Pole and its magnetic poles are not in the same place. How far off? Well, it depends on where you are. I'm in Southern California over here, and I am something like 11.07 degrees east of north with my compass. In Raleigh, yours points 9.3, I moved, you went way too far. Yours points 9, your compass is point 9.39 degrees west of north. So my compass is 20 degrees out of whack with yours. The geographic North Pole sits in the middle of the Arctic Sea and the North Magnetic Pole halfway down to Hudson's Bay, Canada. You can look at this map of the compass cross sections to see how big the difference was in the year 2000. And while we note the differences between these two North Poles are as much as 360 miles and South Poles as much as 1,800 miles, even weirder to note that at 1,800 and 360 are not the same number. The North Poles and the South Poles are not symmetrical. We're not spinning around them evenly. And we're not the only planet with a mismatch between geographic and magnetic norths. I have no idea what's going on Neptune. Its spin, its geographic. Look at that. I mean, it hardly looks like it's part of the planet. And the sun has a huge magnetic field, and it too, therefore, has a north magnetic pole. This gives the whole solar system a north pole and a south pole. And yes, it is, of course, some 23 degrees off our own magnetic north and south. And although the galaxy itself has a magnetic field and therefore a north and south of its own. If north is defined by the right-hand thumb rule, which depends on rotation, movement, and everything is moving somehow one another in this way, there is no real reference for north. And if up is defined by north, there is no up. But that did not deter scientists, you know them, from trying to define an international celestial reference framework. They took 212 very distant objects, those that are so far away that they can be considered pretty much stationary. Then they mapped the coordinates of all of those objects and everything else we can see out in the universe in relation to that frame. With this figure, we can have a static frame of reference. So at last, we've got a static frame of reference, and then, but even this frame of reference moves about 250 microseconds of noise and 20 microseconds of axis stability. That is, it too is moving. With this frame of reference, we can measure relationships between one point in the frame of reference and another. Therefore, we can define north. For convenience, they did align north with the same standard that was used by astronomers already. But of course, that is changing. That is why we have J 1950, J 2000, and J now. These are all coordinate changes. And just to tell you how this reference is permanent and everlasting, realize that it became effective in January of 1998. And now we're in current revision ICRF 3. If the standard were a standard, it would be unchanging. Why has it been revised? Well, because we have better data and we can make better readings, but also, of course, because the celestial bodies referenced in the frame have moved. So it's good, but it's not very good. Not very good, just good. So we have lots of kinds of north, and we can define them in different ways. And really, they are very useful on a day-to-day basis, but none of them, including the International Celestial Reference Frame, are final, true, and unchanging. None of them define up. So let's turn to our last hope, gravity. After all, up is pretty much the opposite of down, where things go when they fall. Down is the attractor, up is the opposite. Engineers have a definite and clear way to describe down, the direction of free weight falls in a vacuum, and we know the opposite of that would be up. Down must be the center of the earth and up the opposite of wherever that is. Except, of course, the center of mass of the earth is a position, and gravity is based on mass, not on position. Earth has multiple centers of mass, and they're not centered, and inertia affects falling. So we've got to examine this and just how good is a standard of gravity. Lunar and solar masses can change down. For instance, right now, you guys are pulling on the sun that many meters per second. You are pulling the sun towards you. It is also pulling you towards the sun, that many. All right? It's 240 quadzillionths, it said. I don't know if that's true or not, but which way the sun pulls you depends on the time of day, or more specifically, the location of the sun. The moon will add to the sun's pull or subtract from it at new and full phases, and that will affect how minimized, and that effect is minimized at the quarter phases. And it too changes depending on the time of day, and how much it pulls you down depends on where you are on the surface of the earth and whether it's in its orbit and where the moon is in its orbit. These factors change the forces of the moon's pull on you because either these are closer or further from you. And what about that 747? Everything is pulling at you at the same time. Jupiter is pulling, it's not time for the 747 yet. Jupiter is pulling you on right now. If there were only you and Jupiter in this universe, you would right now be accelerating at the rate of about 364 nanometers per second down towards Jupiter. You can find calculators of this kind of stuff online. Put in the relative masses of the bodies, you and Jupiter, and the relative distance between the two of you, and apply the formula, and you can get how much it's pulling on you. But like I said, a 747, is that the 747? Yeah, the 747 flying along at 36,000 feet is also pulling at you. If you had that 747 fly 30 feet over your head, it would have the same gravitational pulling effect that Jupiter itself has on you right now. Of course, if it were a 747 flying 30 feet over your head, with the aerodynamic buffering, it would probably make more of an impression on you on that great big distant Jupiter. Point is, you can't just assume there is one down based on gravity. Every piece of maths is to some degree or another down if that is your working definition. And the opposite would be up, but it changes. What we weigh is determined by which way and how much we are being pulled down. Everything else being equal, the difference between our weight at midnight and at noon is about 9/100ths of a pound. Because at midnight, the sun is on the other side of the earth, pulling us harder down to the earth's center, and at noon, it is overhead, pulling us away from the earth's center. The moon is responsible for about 5/10,000ths of a pound of our weight, and Jupiter is 56/10 millionths. So there is not just one down as measured by gravity. Oh dear. In the case of the Earth, we can be affected completely, 100%, one full circle, or 1,296,000 arc seconds. For Jupiter and Mars, it's not that much. The moon can pull us 4 arc seconds off, and the sun can pull us 729 arc seconds, 1/5 of a degree. That is very substantial and really affects our definition of down. If down is where gravity pulls us, just to put that in perspective, and if you're an astrometer, it may move your target from dead center to the edge of your camera frame or even off the frame. But let's ignore for a bit the other masses in our solar system. Earth itself is not a uniform mass. The European Space Agency has sent a spaceship around the Earth orbiting over and over with sensors that can tell how much mass is directly underneath the satellite. This gravimetry found that the Earth is lumpy, much denser and higher masses in some places than in others. Mapped out, it looks like this, not a smooth ball of even description. So what does it matter? Well, water flows, right? So it seeks the lowest level. It flows down. But if down is not consistently in the same place because of the mass concentrations, the level at which water seeks will not be at the same level. So how high up are you today in Raleigh, North Carolina? You're 331 feet above sea level. But what is mean, AMSL, above mean sea level? But what is sea level? A solid lump of heavy molten iron or basalt near Indonesia. Where is that? Over here. Near Indonesia are actually found all over the world on a smaller scale. A few hundred miles can move somebody to an area under the effect of a mascon and raise the average sea level a few feet. So again, how high is Raleigh? 331 feet. But notice the swiggle word in that definition of median, above mean sea level. In fact, scientists regularly must take soundings at thousands of places throughout the world, and they statistically manipulate them to come up with enough markers to define what we think is sea level. How much do these undulations really matter? Well, it makes for a difference of about 3 arc seconds on where down would be. Depending on where you were on Earth, lumpy, dense parts of the Earth pull you down that far in one direction or some other direction. And we know that 3.7 arc seconds is a big variance by scientific standards. Mass, however, is not the only problem we have by defining as the opposite of down, or where something falls when it drops. You see, because we are also spinning, there you go, start spinning, our rotational energy changes with something where something goes when it is stopped. When a kid drops something and it's stopped, it falls right there. It falls right there next to him, right? But as the ride gets going, you can see that rotational speed and the tendencies of things to stay in motion causes things to fly somewhere other than where they might have been when down. They fly out away. Okay. It's the same kid were to drop a backpack here, it wouldn't fall to the ground. It would continue outward and downward. So if you're sitting, it actually continues in a straight line from that position. So if we're sitting here on Earth, we might have thought this is down, but we are in fact spinning around, and that brings down away from where we thought it would be. And of course, this matters to the tune of more than half a degree. The Earth is fatter across its axis of rotation. So am I, but it's fatter than it is through its geographic poles. It's a distance of some 42 kilometers. We're wider by 26 miles than we are tall. That is why the tallest mountain on Earth, when measured from the center of the Earth, is Chimborazo at 20,548 feet above sea level. It is the highest mountain on Earth, not Mount Everest at 29,028. I'll be in Chimborazo next 2 weeks from now. This rotational energy and the bulge it creates around the Earth's equators means that if the rotation were stopped and the water all flowed to the lower points, we would have a dry equator and two polar seas. Of course, this would not last forever, as everything would balance out. So gravity and which way is down does not seem to tell us which way is up. So let's all agree that it's hard to come up with a perfectly defined direction of up. Now, don't get depressed about that. Don't just chill, okay? Practically speaking, we have managed to survive a long time without the important facts I presented today, really complicating our lives. Let's go out of here on an upbeat mood. We'll keep looking up, wherever that might be. Okay? Thank you. I can't hear you.
Thank you very much, Alex. I will try
You're
not to
welcome.
stay in front of camera this time. Does anybody have any questions for Alex?
Don't ask me which way's up, please. Don't ask me.
Okay, got a couple of questions. Hang on.
Alex, you said that I could go online and I could get that comparative calculator to determine, as I
Yeah.
understand it, the
I'll
gravitation
go look. I'll go. Yeah.
of another
Uh,
on me.
you want a link for that? Yeah. Let me. What am I going to do here? I'm going to minimize a little bit of this, and I'm going to. Yeah, I'll go looking. I got to end the slideshow. Okay, I'm back, and we're going to run back up there. That
And you can always email it back to me and we can post it later.
I should have it here,
Okay.
but I will get there. It is. And you know what? You're not going to be able to read this because I always put my references rather small. Okay, I will send it over. It's astro.uni.edu classification. I wonder what happens if I do that. Okay. Anyway, let's go on to the next question.
Hey, Alex. My name's Doug Lively with the club.
Hi.
So a real question. I see you're an astrophotographer yourself. So when you're and I see that you're using a Celestron unit. So when you're setting your guide stars and stuff on your screen, what are you doing? I mean, what are you choosing when you need to? We still need cardinal points to move the star left or right. That does even though there is no up down in space, that certainly plays into actually getting your unit aligned. So
Okay.
what's a poor
Well,
amateur photographer to do?
okay, I want to see a show of hands that everybody heard me at the very beginning where I said none of this stuff matters, and at the very end where I said we've been living with this stuff for years and none of it matters. And I see no hands. So let me repeat that. I want to see a show. No, seriously, where do I point my scope? I tell Nina to go do all that stuff. You know, um, I just because a frame of reference is not perfect or stable or everlasting or eternal does not mean it's not useful. I mean, if the cop pulls you over for not making a left turn tonight and you start quoting what I said, you're going to have problems. So
All right. Well,
where do I point my scope? I point my scope where the coordinates say to point it and then correct it as needed. Yeah.
all right. Moving on to the next question. Give me a second.
Yeah, I do the same thing. That's my job at my meeting. We've got two of us and one chases one side, the other chases the other side. I'm the other side. Go ahead.
Sorry, just a Riverside question. How is Mount Rubidoux this time of year?
It's hot. Okay, we've been having a heat wave, but it's 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 about as flowery as it's gonna get. We had a lot of rain in January and stuff. But as you know, it's dry and dusty in general, but it hasn't gotten there yet. I haven't been up to the top of it in probably 3, 4, 5 years. Now probably 5 or 8 years. Probably before COVID, yeah. Anyway, but I've been up there lots of times.
Anyone else have any questions? Oh,
Oh,
you're
good.
up.
So here's my question. I think you mentioned, and if I'm not correct, let me know that the galaxy has a magnetic north and south. Is that correct?
The what has one? The Galaxy, yes.
The galaxy does.
Yes,
Now, how
yes.
does that happen? Is it the rotation of the galaxy that make them magnetic?
Well,
You may not know this,
yeah,
but
yeah, I don't know the specifics of it, but whenever you have moving metal, a moving,
right.
ferrous metal, and there's a lot of it out in the galaxy, and it does have a general direction of going, in a motion. So now the apparently the galactic magnetic field is very, very weak. It's hard to tell. And I don't know this. I'm not a scientist, just I'm just an old English teacher that got into astronomy. So that's all.
Any other questions?
Uh,
No,
Um,
looks like
will they be able to get to the chat? Because what I plan to do for the question on where you find the those formula, I've got it here, and I can just put it in chat. Would that give everybody access to it?
Naveen can forward that. Also, that's a good question. Are there any questions in the chat? No? Okay. All right. Well, thank you very much, Alex.
Okay, you're welcome. Thank you.
All right. So we're going to go ahead and take a quick 5-minute break before we start the rest of the business meeting. So again, thank you very much, Alex. Very enjoyable presentation.